得主李安哲带来的全英文物理报告。
Hello, ladies and gentlemen. Good afternoon. My name is Andrew Lee. I'm one of the good genes confirmed by our biology teacher. So I hope you're awake today because I'm going to be reporting on quantized states of local motion. So as you can see, this is an IYPT problem. If we oscillate the center of the string with two balls attached, the balls will start to collide and oscillate with increasing amplitudes. So in this report, we'll be thoroughly investigating this phenomenon. This is a full overview of my presentation, and let us begin with the setup and equations of motion. We use a reciprocating machine with hamstrings and 3D printed balls. Here are the contributing factors. We first assume the motion of the pivot can be estimated as a simple harmonic. Then, through second derivative, we can get the effective gravitational acceleration. We then consider the condition for string rigidity by using the relative acceleration. We can separate this term into 4 quadrants, noting that only quadrant 1 and quadrant 3 is valid for our equations of motion. We then consider the finite size inertia of the ball. Then we can get the equation for a single pendulum, accounting for damping and gravity modulation. We then consider inelastic collision by using a collision condition and the coefficient of restitution. Lastly, we discretize the process using Euler's method. For the coefficients, we have characterized damping and the coefficient of restitution with Blake experiments. Thus summing up our theory. Next, let's move on to my qualitative explanations. In my experimental data, as the frequency ratio reaches to 2, we can see a clear increase in the amplitude. Well, at exactly 2, the system damps out at resonance breaks, demonstrating a frequency ratio match in the system. Interestingly, we can see that the collision will always happen at the highest point of the pivot, while a large angle will always occur at the pivot's lowest point. This is the phase difference in the phenomenon. We can explain this using parametric resonance, as a larger gravity will couple with larger sine theta, and the opposite effect will occur coupling with smaller sine theta. Thus, both the positive work and the negative work will increase. So we can draw the potential fields. Accounting for gravity modulation, we can see the trajectory of the lato-lato ball will align with the gradient of the potential. This means the energy is most conserved. Writing down the energy equation, we can note that the dissipation will increase if the amplitude increases. When this term reaches an equilibrium, a steady state will be reached. Next, let's move on to the amplitude fluctuations. We have analyzed the experimental video, and after plugging in the initial conditions, we can see a good experimental agreement. Taking the discrete Fourier transform, we can see a complex harmonic forming with a popnet beat. Zooming into these 2 peaks, we can see that there are the natural frequency and the driving frequency respectively. While the difference between the 2 peaks means that the 2 modes of motion is the amplitude oscillation frequency of the system. Plotting the phase space diagram, we can notice a limit cycle forming. This is due to the amplitude fluctuating with a plus and minus epsilon, as the epsilon will converge to the energy steady state that I have previously mentioned. We are also able to obtain a Floquet multiplier smaller than 1, indicating a stable orbit. Then we can analyze the stable state oscillations after we've done the experiment for a long time. Plugging in the initial conditions, we can see a good agreement. Interestingly, we can also see a symmetric collision point oscillation. As we can see in the discrete Fourier transform, there is a new non-harmonic peak. This peak is caused by the center of mass oscillating like a simple pendulum, thus giving us this new frequency. So we can conclude this part by analyzing the energy. We can note that inelastic collision is the main source of dissipation in this phenomenon. Then let's move on to the dynamical driving frequency. With different driving speeds, there will be a different steady state amplitude. This is called a jump resonance. When we increase the driving speed, we can see that the amplitude decreases. However, if we decrease the driving frequency from the initiation frequency, some previously not possible amplitudes would become possible. This is because the energy here is sufficient enough to maintain the system, but not sufficient enough to initiate it, thus giving us a hysteresis in this phenomenon. We have verified this using a 25 centimeter, 35, and 45 centimeter strings. Analyzing the difference of the string length, we can see that for smaller string lengths, we can reach larger amplitudes. This is because for the same gravitational potential, smaller string lengths can reach bigger amplitudes. Lastly, we can draw a phase diagram with the all reaction, hysteresis, and no reaction region respectively. We can note an increasing amplitude when we move from this region into this region. Well, this is the increase in the omega zero as we have altered the string length. Lastly, let's talk about the Fourier insights. With different driving frequencies, we give it a range of initial conditions. We then ran the simulation for a long time until a steady state was reached. We can see multiple steady states forming at y equals kx, where k is the integral reciprocal modes of the system. This is due to the possibility of multiple oscillations per collision. However, only k equals 1 is experimentally observed in the string, while the others require a stiff lato-lato. This is due to the string stacking in the phenomenon. As the string presents a unilateral constraint, meaning that it can only pull the ball and not push the ball, thus giving us a stacking criteria. And during stacking movement, the ball will enter unpredictable and free-fall motion, as there is not enough force to go into the ball. However, such constraints are not present in the state, so thus the other steady states will be possible. And lastly, we'll talk about the phase 2 transitions. When we normally play the lato-lato, we slowly reach a stable state by sinking the frequency. Then, we suddenly increase the amplitude for double collision, as we can see in the experimental data. We can explain this using phase transitions. When I said earlier that these two equations of motion, it is the area where the equation of motion is invalid. This means that our ball needs to go around these two areas to get to phase 2. So our optimal strategy will be to move from phase 1, and after a sudden amplitude jump, go to phase 2, demonstrating a phase transition in the phenomenon, while the opposite direction is not possible due to hysteresis. So for the explanation, as the ball reaches to 90 degrees, we suddenly pull down the system, making this turn negative. Thus, the ball will remain calm and safely reach to phase 2. So this is the summary of the phases with single collision, possible states, double collision, and phase 1 failure. So at last, we can summarize this with a quantization of the multiple modes. As we can calculate the average energy, we can get that the difference between these modes are equivalent to a Rydberg equation, meaning that the energy distribution is similar to a hydrogen atom. This also explains why, at these modes, the graph is more dense. In conclusion, we have a good explanation with a potential field, we have a good quantitative agreement with our theory, and we have investigated several parameters and broadened the boundaries in this problem. Here is a full overview of my report. I would like to take some time to thank my supervisors, my family, and all the friends that have supported me along the way. And if there are any questions about IYPD or my projects, I'll be happy to answer in the break. Thank you.
接下来在中场休息前，我们想和大家合照，所以待会会请班题一上台和我们合照。那还没照到的。